vector space of all real polynomials less than equal to 3 together with 0 polynomial over R, determine whether u, v, w belonging to V are linearly independent or linearly dependent, where u, v are given to be as these. So we need to check whether u, v, w are linearly independent or not. The condition for the linearly independency is we just write the linear combinations of them, alpha u plus beta v plus gamma w equal to 0, and then we need to show that these scalars alpha, beta, gamma, all these are equal to 0 for linearly independency, right? So let's check this. So let's first take the linear combinations of these. So let alpha u plus beta v plus gamma w equal to 0. Then just substituting the value of u, v, w which is given to us. And now let's collect the coefficient of x cube. So this is alpha plus beta plus twice of gamma and the x cube plus collecting the coefficient of x square. So this is minus 3 alpha minus beta minus 4 gamma x square. And then 5 alpha plus 8 beta plus 9 gamma x, and then the constant alpha plus twice of beta plus 5 gamma equal to 0, right? We know that this x cube, x square, x and the coefficient 1, these are linearly independent. These are the standard bases, right? So since x cube, x square, x1, these are linearly independent, which means their scalars should be equal to 0, right? What is the scalar for x cube? Alpha plus beta plus twice of gamma. What is the scalar for x square? It is minus 3 alpha minus beta minus 4 gamma, right? So these becomes the scalars for x cube, x square, x and the coefficient. So all these are equal to 0. So all these should equal to 0, right? So writing the scalars, alpha plus beta plus twice of gamma, this should be equal to 0. Minus 3 alpha minus beta minus 4 gamma, this is equal to 0. And 5 alpha plus 8 beta plus 9 gamma, this is equal to 0. And at last, alpha plus twice of beta plus 5 gamma is equal to 0, right? And now we need to get the value of alpha, beta, gamma, and to check that whether these values are equal to 0 or not, because for the linearly independency, if I take the linear combinations of u, v, w, then their scalars should be equal to 0 for the condition of linearly independency, right? So I'm getting all these linear equations and I need to check whether alpha, beta, gamma are coming out to be 0 or not. For that, just writing this in another format, writing the coefficient matrix, and here alpha, beta, gamma, that is equal to 0, 0, 0, 0, right? Okay. So the first row becomes 1, 1, 2. Then minus 3, minus 1, minus 4, right? So this is 1, 1, 2, minus 3, minus 1, minus 4, and then 5, 8, 9, and then 1, 2, 5. Writing here alpha, beta and gamma, and here 0, 0, 0, 0, because we are having 4 linear equations. So let's take this to be as your matrix A, and we need to reduce this matrix into the row echelon form, right? So let A is equal to 1, 1, 2, minus 3, minus 1, minus 4, 5, 8, 9, 1, 2, 5. Is it okay? Fine? Okay. Let's reduce this to the row echelon matrix. I'm having in the first row the leading entry as 1. To make this a leading element, I need to make all these entries to be 0. For that, taking the help of the first row, multiplying the first row with 3 and adding its elements to the second row so that I can get 0 over here. Multiplying the row 1 with negative 5 and adding its element to the third row so that I can get 0 over here. Multiplying the first row with negative 1 and adding its elements to the last row so that I can get 0 over here. So I am applying the 3 operations and getting 0 in place of negative 3, 5 and 1, right? So writing the first row as it is, In the second row, I get 0, 2, 2. In the third row, I get 0, 3, negative 1. And in the fourth row, I get 0, 1, 3. So because all the elements are 0 below the leading entry, so this becomes the leading element for the first row. And now I am having this to be the leading entry for the second row. I need to make this as 1. For that, just multiply the second row with 1/2. So second row now changes to 0, 1, 1. Writing the rest of the rows as it is. And now this becomes a leading entry for the second row. To make this to be your leading element, I need to make these two to be 0. For that, multiplying the second row with negative 3 and adding its elements to the third row so that I can get 0 over here. To get 0 in place of 1, I just multiply this row with negative 1 and adding its elements to the last row. We can also get 0 in place of this 1, but this leading element should not be disturbed while applying the operations. So for that, again I am multiplying the second row with negative 1 and adding its elements to the first row. Right? So again I am applying the three operations together to get 0 in place of 1, 3 and 1. So first row changes to 1, 0, 1. The leading element is not disturbed. Writing the second row as it is. Third row changes to 0, 0, negative 4 and fourth row changes to 0, 0, 2. So this becomes a leading element for the second row. All the elements are 0 below this leading entry. It's good if you also make the above entry to be 0, but for that, leading elements should not be disturbed. Alright, in the third row, I'm having negative 4. So to make this 1, just multiplying this row with negative 1 by 4. So third row changes to 0, 0, 1 and writing the fourth row as it is. So this is the leading entry for the third row. What do you mean by the leading entry? It is the first non-zero entry present in the row that becomes the leading entry for that row, right? Okay. To make this to be the leading element, I need to make this to be 0 and also these two to be 0 if possible, but these leading elements should not be disturbed. For that, just multiplying this row with negative 2 and adding its elements to the last row. Multiplying the same row with negative 1 and adding its elements to the second row and also to the first row. Also multiplying this row with negative 1 and adding its elements to the second row and also adding its elements to the first row so that I can get 0 over here also, right? So I'm applying these three operations again for the third, second and first row. So first row changes to 1, 0, 0. Writing the second row as it is. Second row changes to 0, 1, 0. Writing the third row as it is. And the fourth row changes to 0, 0, 0. So this becomes the leading element for the third row also because all other entries are 0, right? So this is the very beautiful reduced row echelon form, right? Let me mark that system to be 1. This. Please mark this as 1. And replacing this matrix A with the row echelon matrix, the reduced one, the reduced row echelon matrix, right? So therefore the system 1 reduces to 1, 0, 0, 0, 1, 0, 0, 0, 1 and 0, 0, 0. And here we are having alpha, beta and gamma and here 0, 0, 0, 0. If we write back the equations, what we get? Okay. 1 multiplied with alpha plus 0 multiplied with beta plus 0 multiplied with gamma. So this is equal to this 0. That is what we are getting, alpha equal to 0. And now the second equation, 0 multiplied with alpha, 1 multiplied with beta and 0 multiplied with gamma. So we are getting 0 into alpha plus 1 into beta plus 0 into gamma equal to this 0. Third equation, 0 into alpha plus 0 into beta plus 1 into gamma equal to this 0. And fourth one, 0 into alpha plus 0 into beta plus 0 into gamma equal to 0. So we are getting these equations. this equation has no use. So from the first equation we get alpha equal to 0. From the second equation we get beta equal to 0. From the third equation we get gamma equal to 0. So we are getting all these scalars to be 0. That is what we required, right? Okay, so from star, let me mark this to be as star. From star we are having alpha u plus beta v plus gamma w equal to 0. And because alpha equal to beta equal to gamma all are equal to 0, so therefore u, v, w are linearly independent. Right? Okay, thank you. Stay blessed.